All right. Hello, everyone. Hopefully everybody is doing fine. Another week of our classes. Let's go to Canvas. Let me share the screen with you. Go to Canvas. This matrix, it is called element stiffness matrix for a spring element. For a spring element, for this one, we found that element stiffness matrix is like this. This U1, U2, we show it by this D. It is a displacement vector. And F here, this is force vector. These are forces, F1, F2 are forces. This is called force vector. So KD is equal to F. This K is element stiffness matrix. And by the way, it is symmetric. Look at this negative K, this one, and this is the same. So this is symmetric. This is displacement vector, and this is force vector. This is for one element. Now, when we have a combination of elements, put them together, the general formula is KD is equal to F. This was lowercase k. This is uppercase K. This is global for all the spring elements in the system that we have. This is displacement vector for displacement of all nodes in the system, and this is force vector. This is lowercase f for one element. This is global force vector. Okay, D is equal to F. In finite element methods, always our solutions end up like this, KD is equal to F. With this now, let's solve an example problem 215. Any questions before solving?
Yeah.
Problem? Yes.
I have a question. From the model, why do we make F1x negative T?
Well, it is in the opposite direction as this one. This F1x is pointing to the right. F1x pointing to the right. This one, look at this one, it is pointing to the left. So
right. So why don't we just draw it pointing to the left like T is?
This is our finite element model. This is our finite element notation. In finite element notations, to the right, it is positive. So our notation in finite element methods, everything for one-dimensional bars, everything to the right, it is positive. So F1x, U1, F2x, U2, everything to the right, it is positive. This is our finite element notation. This is the notation that we used in solid mechanics, that we said this applied T to this node, it is positive, and this is also T positive if it is in the negative X direction on the other side. So for equilibrium, we use this one in statics. In solid mechanics, we use this notation, that this T is to the right and this T is to the left. This is our notation in finite element methods, that everything to the right is positive. So with this, then our F1x here to the right, it is equal to negative of this T at node 1.
Okay.
All right, any other questions? Time to look at this example problem. You have paper and pencil ready, because we are going to break down the problem into smaller pieces, so you are going to also participate in solving this. So have your paper and pencil ready. Let's look at this problem 15. We have this system of springs, 500 kilonewton per meter, the same, and 1000 kilonewton per meter. They're connected by this block. So this block is not doing anything, just it's on these rollers just to connect these springs and move them horizontally. So it's not doing anything, it's just connecting these springs. We have 3 springs. Determine the nodal displacements. We are applying this 2 kilonewton here and 2 kilonewton here. So total, we are applying 4 kilonewton to this block, and then we are moving it to the right. We want to find the nodal displacements, the forces in each element. We have 3 elements here, 3 springs. So these are 3 elements. We want to find forces in each element and the reactions. These are attached to the wall. So we want to find the reactions. Use the direct stiffness method. We will see what the direct stiffness method we mean by this. So here, again, we want to find nodal displacements, forces, and reactions. First step is always to create discretize the geometry. So we are given this system. Discretize. So this is our finite element model. This is first spring, second spring, and the third one. This is node 1, node 2, node 3, node 4. Element 1, element 2, element 3. So in this problem, we have 4 nodes and we have 3 elements. And this is at node 3, we are applying 4 kilonewton, 2 and 2, 4 kilonewton to the right. So this is our finite element model. Remember, in finite element method, first step is to discretize. We discretize now. First item is to excuse me, create the connectivity table. By connectivity table, we mean that relate each element with its nodes to show how they are connected. So connectivity table, element 1, it shows elements, node I to node I plus 1. So here, element 1 goes from node, this is element 1, goes from node 1 to 3. So 1 to 3. Element 2, look at element 2, goes from node 2 to 3. So this is element 2, goes from node 2 to 3. Element 3 goes from node 3 to 4. Write it down. Element 3 goes from node 3 to 4. So 3 nodes, 4 nodes, I'm sorry, 3 elements. This is called connectivity table, our first step. Next step is to apply this element stiffness matrix. Remember this one that we developed, this one, element stiffness matrix, for each of these elements. So here for element 1, K for element 1, its stiffness was 500. So it is 500, negative 500, negative 500, 500. Here, put the addresses here. This is element 1, goes from node 1 to 3. Put this 1, 3, and 1 and 3. This is for our reference. This and this, these two is just for our reference because we want this and this just to know their addresses. So computer can put them in the right spots. So this is just for our reference. It's nothing to do with this formula here. So that is element stiffness matrix for element 1. You said you have your paper and pencil ready. I want you to do this, the same thing that what we did here for element 2. Write it down. Then after that, we do it for element 3. Write the element stiffness matrix for element 2 and 3. I have also my camera. I got a camera, so let me let me see if okay. This is my camera also. I can write this one here. Do you see the camera on the screen, on your screen?
I
No.
don't.
Yes or no? I didn't hear.
No.
No.
No, you don't see the screen, and I have to share the camera. You see now the camera here?
Yes, sir.
Yes.
Okay, yeah, I have to do one at a time, so I have to switch from this to this. That's fine. Yeah, this is, I want you to, let me see, I started problem 215. We said that this is the model. This is first time I'm using it, so let me see the best way to do this. All right, this is node, this is attached to the wall here. This is attached to the wall, and this is attached to the wall. This is node 1, node 2, node 3, and node 4. Element 1, 2, 3. And I asked you to do this K for element 2. For element 2, we have again the stiffness, we said it is 500. So this is 500, negative 500, negative 500, 500. Goes from what? I should put for element 2, it goes from node 2 to 3. So write 2, 3, 2, 3. It is just for our reference, just to know their addresses, and do it for element 3. What did you get? Element, somebody read it for me. What did you get for element 3?
I got K of element 3 is matrix 1000, negative 1000, and then negative 1000, 1000.
Okay, and the addresses are?
3, 4, and then 3, 4.
Very good. Excellent. Very good. Yes, this is one negative 1000 and 1000, and it goes from node 3 to 4 and from 3 to 4. All right, excellent. Very good. Next step is to create the global stiffness matrix. Now, the global stiffness matrix we need the we need, first of all, these programs need to initialize. We need to know the size of this global stiffness matrix. So the question is, what is the size of this? Because these programs are in C, C++. In C, we need to know the size of a matrix in advance, unlike MATLAB. MATLAB is excellent because it doesn't ask you for what is the size of the matrix. You can just add whatever you want, and it just adjusted itself. But not C or C++. We have to see what size it is. First of all, to initialize this, how many nodes do we have in this? Do we have in this problem? How many nodes?
3.
It's 4 nodes.
4 nodes.
4 nodes. 4 nodes multiplied by how many degree of freedom per node? I need a degree of freedom per node. In other words, at each node, how many unknowns do we have? Just displacement in the x direction. Is it each node? Suppose, of course, this is a smaller one. Once we develop our solution, then we can do it for bigger systems. But each node has a displacement in the x direction. So we have just 1 degree of freedom per node. Each node has this displacement in 1 direction. So 4 nodes times 1 degree of freedom per node makes it 4 degree of freedom. So this problem is has a 4 degree of freedom, which means that our global stiffness matrix Remember, we showed it by K. K is our global stiffness matrix. It is
Question?
yes, 4x4 matrix. Yes, question?
So even though the like node 1, 2, and 4 are fixed in location, they still have a degree of freedom.
We write them down, then we apply the boundary conditions, we
Okay.
will remove them later. But always, yes, this system doesn't know at the beginning, this computer doesn't know if node 2 or 4, they are attached to a wall or not. They don't, it doesn't know. It just, we identify these nodes because then we know what element is connected by what nodes. So we are just defining our system at this point. Then we apply the boundary conditions to specify that they are attached to these walls. All right, clear?
Yeah, thank you.
All right, sure. Now, global stiffness matrix. So let's, we need to create a, let me do this here. So our K, just open one matrix, one big matrix here, and then call it, yeah, this is, we have 4 nodes. So it is 1, 2, 3, 4, and it is 1, 2, 3, 4. Now, time to plug each of these in the right spot. I didn't write it for node 1. So node 1, we said very similar to this one. I didn't write it down. It goes from node 1 to 3. So this goes 1 and 3, 1 and 3. So this comes here, this 500, negative 500. This is node 3, negative 500 and 500. This is for element 1 goes and sits right this here in the global stiffness matrix. All right, clear? This is the address. That's what we wanted, 1 and 3. So we know the address here. Do the same thing for elements 2 and 3. That is your part. Tell me, write it down, feel it for elements 2 and 3. Take the element stiffness matrix and dump them in the right spots in the global stiffness matrix. All right, did you do this?
Yeah.
Now tell me what, for element 2, look at this element 2, it goes from node 2 to 3, 2 to 3. So I have to put this one, 500, negative 500, 2 to 3. So negative 500, 500. It adds it to this one because previously I had one, so it adds it to the previous one. And for element 3, it goes from node 3 to 4. So 3 and 4, it comes here. So it adds another plus 1,000. I'm running a little bit out of space here. Sorry for, I should have opened it a bigger one. Let me see, it is negative 1,000, 1,000, 1,000. All right,
Isn't
Right.
3, 4 negative 1,000?
I'm sorry. Negative, is it what you mean? Yes.
Yeah.
Yes, very good. Thank you. Yes, 1,000, negative 1,000, negative 1,000, 1,000. That is for element 3. It sits here, and then the rest 0 here. Everything else is 0. So these are all 0. And this last one, 0, 0, negative 1,000, 1,000. This is the global stiffness matrix, and very important step in our finite element solution of this problem. Any questions about this? Any questions about this? All right. If not, then let me go back to our. Yeah, I have to switch back and forth. Switch. Let me share the screen with you. Now you see the spring element back to our canvas, right or not? On your screen, what do you see?
Yes.
Okay, this is the, sometimes I go back and forth with this camera. By the way, how is this camera working? This is first time I actually got it, and how do you think like this with this camera?
It was super clear.
Pretty good.
Good, you follow better with this, I think.
Yes.
Okay.
Yeah.
Okay, very good. This is first time actually I'm using this. I got it a couple of days ago. The day before yesterday, I received it. Okay, so this is the our finite element model. These are the element stiffness matrices. The global formula is KD is equal to F, and this is our global stiffness matrix. It is called by direct stiffness method. That's what you see. We directly dump them in the right spots. But there are other methods, but which is not, we have to use equilibrium for each node, and it is lengthy. But this is the very straightforward and simple to apply. This is our global stiffness matrix that we now wrote it down, and our system of equations is now like this. Just adding them together, it is 2,000. This is our global stiffness matrix times displacement vector is equal to force vector. Remember, this is our global formula. Very important. And next step is to apply boundary conditions. The problem is not defined yet here. You see, it is not, we still don't know what forces we are applied to what nodes and how we are fixing this. So it's not defined. Time to apply boundary conditions. The boundary conditions are displacements at node, look at the figure, displacements at node 1, 2, and 4 are 0. If displacements are 0, they are called homogeneous boundary conditions. Remove them from the system of equations. So, for example, node 1 displacement is 0. Row 1, column 1 out. At node 2 displacement is 0. Row 2, column 2 out. Node 4, 0. Row 4, column 4 out. So these are the displacement boundary conditions. Now, this was F3X, remember here, but at node 3, we are applying 4 kilonewton here. F3 is equal to 4. This is the external force we are applying. This is force boundary conditions. This is the only one. That's it. The system is now ready to be solved. We removed almost everything except just this one. Of course, it was just by hand. We are making it a simple problem by hand. But remember, computers can do it hundreds of thousands of elements. So we end up with a very large system of equations for Nastran to solve. But here, just by hand, we ended up with just one equation here. 2,000 times U3 is equal to 4, is this. And we solve for U3, it is this one. Therefore, to answer the question, to find displacements at nodes, these are the displacement, node 1, 2, and 4, 0, and node 3, we found this to be 0.002. That is the solution to part A of this problem. Any questions? It is important. I want you to understand this because as we move forward in this class, then other cases, we use this technique by direct stiffness method, applying boundary conditions, force boundary condition, displacement boundary condition. So I want this to be clear so we don't have problems later. Any questions at this time?
No, it seems pretty clear.
All right. So let's move on. Part A of the problem is clear, is solved. Now part B, to find forces in each element. Our solver's job is actually finished. At this time, Nastran has finished finding displacement. Everything else is now post-processing, not a big deal. Find forces in each element. Use the elemental formula. We are out of global. That was the global formula. This is the for each element. KD is equal to F. K is our element stiffness matrix. For element 1, this is just for element 1 now. Just look at element 1. It is K1, negative K1, negative K1, K1. Node 1, element 1, node 1, and node 3, according to our connectivity table. Remember here, this connectivity table, it gives for element 1, nodes 1 and 3. So this node 1 and 3 go here, U1, U3. Force vector at node 1 in the x direction, at node 3 in the x direction, and this is for element 1. So we put here 1 just to specify this element 1. With this now, just multiply. It is not, we are not solving this system of equation. We are just multiplying this matrix by this matrix, this row times this column, get this one, and for element, for node 3, multiply this one by this, we get force at node 3 in the x direction. For element 1, it is 1 kilonewton. These are the forces in element 1. Now I would like you to do it for element 2 for me. Do it for element 2, and then we are going to do it for element 3. Apply this formula for element 2. Tell me what are the forces in element 2. You have 2 minutes. Tell me what you get. All right, anyone? For element 2, what are the forces in element 2?
The same as element 1.
Same as element 1. Anyone agrees with your friend or not?
Yeah, it's the same, but obviously with at location 2.
Very good, you're right. So this is for element 2. This is the element stiffness matrix for element 2. Displacements would be for node 2 to 3. Element 2 goes from node 2 to 3, and these are the forces. And plug the numbers, very similar to element 1, and multiplying, we get force at node 2 in the x direction, negative 1 kilonewton, and at node 3, 1 kilonewton. and do it for element 3. For element 3, this is K3, negative K3, negative K3, K3. Displacement U3, U4, it is equal to force vector. Displacements of node 3 and 4, we found for displacement of node 3 already. That was 0.002, and this node 4, it is attached to the wall. This is the force vector. Multiplying, we get 2 and negative 2. All right. Any questions so far before moving on to the next step, which is finding the reaction forces? What we did, we found forces in each element. Now, to find reaction forces, again, these are all post-processing. The solver's job was finished when we found the displacements. This is the post-processing. The question is to find the reaction forces. We use the global formula to find the reaction forces. Use the global formula KD is equal to F. This is the global stiffness matrix that we found. Very important step in finite element analysis. Times displacement vector, node 1, 0, node 2, node 3 displacement, we found this, and node 4, 0. It is equal to force vector. This is at node 1, node 2, node 3, and node 4. Remember our model here, node 1, this is a reaction. This is attached to the wall. We don't know what this reaction force is. That's the question. Node 2, node 3, we already know that this is an internal node. We are applying an external force of 4 kilonewton here. And node 4, there is no, it is attached to the wall. So we have 4 nodes here, but this one is known value. So going back to this, we put 4 for this node 3, multiplying this row times this column, we get reaction at node 1, negative 1, and at node 2, we get negative 1. For this third equation, we already know this, so it checks. It is just to make sure that we have done it correctly. If we have made a mistake, it will show it here. But we already know the value of this, what we should get, and it checks that we have done it correctly. And for the last one, last row times this column, we get reaction at node 4, we get negative 2. These are the reaction forces that we wanted to find. All right. There is one last thing. In finite element analysis, we always need to verify our solutions. We do not solve a problem without somehow checking whether we have done it correctly or not. We cannot be, these computers just give some trash in, trash out, garbage in, garbage out, they call it. You can just give some numbers and it gives you some number, nonsense numbers back. We have to make sure that we have done it correctly. We need to verify our solution. Verification in this case, it is done by equilibrium. Make sure equilibrium is satisfied. So draw a free body diagram. This is free body diagram of this spring system that we had. This is node 1, 2, 3, and 4. Node 3, 4 kilonewton force applied. At node 1, we found this force reaction at node 1, negative 1 kilonewton. This is 1 kilonewton to the left. The same node 2, 1 kilonewton to the left. And at node 4, negative 2. This is 2 kilonewton again to the left. Is equilibrium satisfied here? Sum of forces in the x direction to be 0, negative 1, 4, and negative 2. Yes, equilibrium is satisfied. This is how we verify and validate our solution. Without this, it is not good. We should always find ways to verify our solution. All right, that was our example problem. Any questions on this? No questions? Which means we are ready to continue. Now, the next step, we are not going to, the next discussion would be talking about trusses. But before that, I would like to review matrices. In finite element analysis, we use matrices a lot because computers work with arrays of numbers, with matrices. So to review matrices, that's, you had it before. I'm just reviewing it. It is not something new I'm lecturing. It is just review what you already have from your math 224. I think you had before differential equations and linear algebra. So it's just reviewing. Any questions? Always feel free to discuss. I don't want to talk all the time. I want you to participate, be active in your learning, and ask questions. Anytime you have questions, feel free to ask questions. Now, this is a matrix. It is n by m. This has n rows and m columns. This matrix is called an n by m matrix. This matrix, on the other hand, is an array of only one column. So this is called a column vector, or just simply some people call it just a vector, but the better term would be a column vector, because sometimes we have a row vector. If this has one column, but sometimes we have one row, but multiple columns, m columns. So in that case, we call it a row vector. So this is a column vector. So a matrix n by m, as you see here, this refers to number of rows, this refers to number of columns. For example, this matrix A, a couple of simple example questions. What is the term, you see an m here, this first n refers to the number of row, and m here refers to the column. So if somebody asked, what is this? First of all, what is the size of this matrix? What would you say? What is the size of this matrix? Question for you.
3 by 4.
3 by 4, very good. It has 3 rows and 4 columns. Then the question is, circle the correct answer. It is a 4 by 3 or 3 by 4 or 4 by 4. So this is just 3 by 4. You said term 3, 3, a 3 comma 3. This first term, this third 3 refers to the row number, column number. So 3, 3 refers to this one. This is row 3, column 3. So row A3, 3 is 7. This is this number. Which matrix B can be multiplied by A? I think in the activity you did it also here in activity 1, which is due this Wednesday. Matrix A is given here. Which matrix B can be multiplied by A? For example, can we multiply A times B? No, it has 4 columns. Should match with the number of rows here. It doesn't. So this number of columns should match the number of rows here. It doesn't. So we cannot multiply it by this B. By this one, no, we can't multiply. This one, yes, we can multiply. It has 4 rows and it has 4 columns. It has 4 columns. It has 4 rows. Then yes, we can multiply this. This is the right answer. Calculate C, just multiplying this matrix A times matrix B. It is a homework for you. You can do it later yourself. So multiplying these matrices, just to remember how we add, subtract, or multiply matrices. Calculate A transpose times A. A transpose, replace the rows and columns in a matrix. This is transpose of this. So for example, if this is matrix A transpose means that row 1, 4203, column 1, 4203. Row 2 of matrix A, 1623, column 2, 1623. And the same, row 3, column 3. So A transpose times A, that again for you to do this. These are just some simple operations for matrices. This week, actually, we are going to in the lab activity that we have this week, activity 2, we are going to solve simultaneous linear equations by Gauss-Jordan elimination method or by other methods. But today we are going to use actually one of the most popular ones. The most programs actually use Gauss-Jordan elimination method. We are going to review this. You had this one, or you had previously, possibly you had Gauss elimination, but Gauss-Jordan elimination is maybe, it is continuation of Gauss. So if you had it Gauss before, then we are going to continue with Gauss-Jordan. By this method, we solve a system of equations in 2 steps, normalizing and pivoting. So look at an example problem here. 3 equations, 3 unknowns. X1 plus 2x2 plus 3x3 is 4. So this one equation, 3 equations and 3 unknowns. We want to solve this system of equations by Gauss-Jordan elimination method. Gauss-Jordan or row reduction. Some people also call it row reduction method. So by this method, we create the augmented matrix. This is the augmented matrix, which is the same, these coefficients, coefficient 1, 2, 3 here, 1, 2, 3, and we add this right-hand side to this matrix. So that's what it's called, augmented matrix. We augment the coefficient matrix actually with this right-hand side. So 4 to 7, it goes 4 to 7 here. So this is the augmented matrix. Now we use 2 properties that matrices have in order to solve this system of equations. We use 2 properties of matrices. One property is that we can always multiply a row or divide a row by any number. It doesn't change the result of this system of equations. So you can multiply this row or divide it by any number, it doesn't change anything. And the second property is that you can multiply it or divide it by any row and add it or subtract it to another row and it doesn't change anything again. So these 2 properties we are going to use to solve this system of equations by Gauss-Jordan elimination method. To do this, again, we said 2 steps, normalizing and pivoting. Normalize, meaning make this term 1. If it was not 1, it is already 1 here. So we don't need to normalize. It's already normalized. So we are fine here. So first step, we are done normalizing this first term. It is fine. Pivoting means this term that we normalized, use it as a pivot element to make this term and this term 0. How can we do that? Well, if you multiply this by -1, add it to this one, it makes it 0. We said that we can multiply any row by any number and add it to another one, it's the same. So, okay, then multiply this row by -1 and add it to this one, it makes it 0. And multiply this row by -2, this -2, multiply this row and add it to this one, it makes this 0. So if we do this, we get this. These two are now 0. That's what we wanted. We end up with this matrix. Next step is to look at this diagonal term here. This one, I want to make it 1, normalizing. Again, remember 2 steps. Always we go normalize, pivot, normalize, pivot. I want to make this term 1. What should I do? Question for you. I want to make this term 1. What should I do? Question for you. Somebody tell me.
You could multiply the third row by, you want to make it 1 to make, I guess you just multiply it by -1/3.
Very good. You're right. This is multiply this row, second row, by -1/3 makes this one 1. Okay, so we don't touch anything to the first row. So this 1, 2, 3, 4, this 1, 2, 3, 4. This row multiplied by -1/3. So -1/3 times 0, it is 0. -1/3 times this one, it is 1. -1/3 times 2, it is -2/3. -1/3 times -2, it is 2/3. It is this one. And leave the third row as it was. So it is 0, -1, -2, and -1. We are not doing anything to this. Now that we did the normalizing, time to pivot. Use this one as a pivot element to make this one 0. How do we do this? Well, in this case, we can just add them together, or better to show the procedure, we multiply it by 1 and add it to this one. So add this row to this row. This is this one, we get this. Leave the first row the same. This one, it is the same. And this one, when we add this one to this, we get 1 and -1, 0. -2/3 and -2, it is -8/3. And 2/3 and -1, -1/3. This is the matrix we get. Done with pivoting, now time to normalize. We need to make this 1. Multiply it by this, inverse of this. It is this one. To make it 1, we get this one. It is row 1 is the same, row 2 is the same, and this one, just multiplying it by this number, we get this one. That is what you look at this elements. These elements are all 0. These are lower triangular elements. Lower triangular elements are all 0. And diagonal terms are all 1. That's what we wanted to achieve. Next step is to do the same thing for upper triangular elements, for these elements. I want to make these elements 0. To do this, use this one as a pivot element, make this one 0. Again, use this as a pivot element to make this one 0. So to first make this one 0, what do? I multiply it by just 2/3, add it to this one. This is this 2/3 multiplied by to this row and add it to this one, makes this 0. And for making this one 0, I multiply this row by -3, add it to this one, makes this 0. So if we do this is pivoting, as you see, we are using this as a pivot element to make this 0. The result is this, we make this to 0. Final step, make this 0. Well, simply multiply it by -2 and add it to this one, makes this 0. So multiply this row by -2, add it to this row. This is this. What does it mean? All lower triangular elements 0, upper triangular elements 0, diagonal terms 1. Well, we arrived at the solution actually. This is our x1, this is our x2, this is our x3. This is the solution. x1, x2, and x3 here. This is the solution. Most computer programs actually use this Gauss-Jordan elimination method to solve system of equations. All right, any questions on this before looking at another example? No questions on this. Just one point here. You see, this is called lower triangular element 0. Some programs stop here actually. By Gauss elimination method, we stop here and we do back substitution. From here, this is already x3. We use x3 in the second equation to find x2. Then we go and use x2 and x3 in the first equation now to find x1. So this is back substitution. If we want to stop here by Gauss method. But Gauss-Jordan elimination method, if we continue like what we did here, make these upper triangular elements also 0, then we don't need to do back substitution. We already have the solution now. All right. Let's look at another example problem. I want you to do one piece of this for me here. This is the simultaneous linear equations again. 4 equations for unknowns. This is called the coefficient matrix, displacement vector, right-hand side. Coefficient matrix, we know. These are the values we know. This is the displacement vector, the unknown. And this is the known, right-hand side, we know. We want to solve for this unknown vector, or U1, U2, U3, U4. This is the matrix. First step is to do what? Question for you. What should I do first?
Normalize.
No, before normalizing, I have to do something else.
Oh, create the augmented matrix.
Very good, you're right. Create the augmented matrix. That is your job. 1 minute, write it down, write the augmented matrix for me. All right. This is the augmented matrix. 1, 0, 0, 0, and another 0 adding to this one. The same, add this column to this coefficient matrix like this. Next step, we need to, this is already normalized here. This is already 1. This is already normalized. We need to use this as a pivot to make this 0. In order to do this, I need to multiply this row by 9 and add it to this one. Do this operation for me. We are going to do this on Wednesday, actually, for the activity, solution of simultaneous linear equation. This is by Gauss-Jordan elimination method. Now multiply this row by 9 and add it to this one to make this 0. 1 minute, do this, write it down. All right, we do this one, 9 multiplied by this one, 9 times 1, and add to this one, we get 0 here. And the rest is this 0. So actually we have 11, negative 2, 0, 0, the same thing. Now time to normalize this. Normalizing, meaning that I need to make this one 1. I have to divide it by itself or multiply it by 1 over that number, whatever it is here. Inverse of that number. So multiply this row by 1 over 11. The result of this matrix doesn't change. It's the same thing. So doing this, we get, first row, we get 1 and zeros, and 1 over 11 multiplied by this, it is 0. 11 times 1 over 11, we get 1. Negative 2 times this, it is negative 2 over 11, and then 0, 0. That is normalized. Next step is to use this as a pivot element to make this one 0. To do this, simply multiply it by 2, this row by 2, and add it to this one. 2 times 1 and negative 2 makes this 0. And the rest you can multiply this 2 times this one, negative 4 over 11, add it to 6. The result is this one. Next step is to make this one 1, normalize. Multiplied by inverse of this, 11 over 62. Multiply this row by this number, makes this 1. Everything else remains the same. This row 1 and row 2 remain the same. Last row remains the same as what you see here. This row is the same as this one. It is just this one changes. Multiplying this row by this number, we get this. And next step is to, what should I do? 1. I have to use this as a pivot element to make this term 0. Multiply it by 5 and add it to this one, makes this 0 here. Makes this 0 here. And finally, this diagonal term, this one, I have to normalize. Make this one 1, just multiply by inverse of this 62 over 35. We get this also 1. So these diagonal terms are all 1. Last step, next step is to make this one 0. I use this as a pivot element to make this one 0. Do this multiplied by 55 over 62, makes this one 0, and finally I want to make this one yes, I want to make this one 0, so multiply this row by 2 over 11, add it to this one, makes this 0 here also. And then the rest is 0. As you see, diagonal terms are all 1. Lower triangular element 0. Upper triangular element 0. This is already the solution actually. This is our x, u1, u2, u3, u4. 0, 16 over 7, 88 over 7, and so on and so forth. And this is the solution of this system of equations. All right, any questions on this? Before looking at one more item today, any questions on this? Gauss-Jordan elimination method or row reduction method? All right, last example problem I have for today, it is inverse of a matrix by row reduction method or Gauss-Jordan elimination method. Again, but inverse of a matrix. I think you had practice for the activity 1, which is also due on Wednesday this week. You did this one, inverse of a matrix by Gauss-Jordan elimination method. Matrix A is given by this. Inverse of this matrix. Create a matrix like this and add this matrix to this. I have separated it with this partition just to make it visible, but to see it easier with this partition. I added this matrix. Tell me, this matrix is called what here? This one is called what?
Identity matrix.
Very good. It's a matrix with all diagonal terms 1, this identity matrix. These terms are all 0, these terms are 0. We are again going to use these two properties of matrices. Multiply any row by any number or divide, you get the same result. And also you can multiply any row or any row by, or divide any row by any number and add to another one, you get the same thing. That is the property of matrices. These two we use to find inverse of this matrix. Do the same as what we did for Gauss-Jordan elimination method. Nothing new is already 1. Normalized. I want to make this one 0 and this one 0. Multiply this row by -2, add to this one, makes this 0. Multiply it by 1, add this one, makes it 0. This is what we get. These two are 0. Next step, normalize, make this 1. Multiply this row by this number, makes it 1. As you see here, use it as a pivot element to make this 0 here. Multiply this by -2, add to this one, makes this 0. And finally, I want to make this one 1, normalize, multiplied by inverse of this one, 3/2, makes this 1. Not done yet. We have to, all lower triangular elements are 0. Go for upper triangular elements. Do it backwards now. Multiplied by -2/3 to make this 0. And multiply it by -1 to make this one 0. So doing this, you get 0 here and 0 here. And finally, I have to make this one 0, multiplied by -2, add it to this one, makes this 0. This is 0. What we did, all upper, lower triangular element 0, upper triangular element 0, diagonal terms all 1. This is inverse of that matrix. inverse of A. A inverse is now this matrix, -1/2, 1, 1, 2, and so on and so forth. All right, that was the last item I wanted to cover today. Any questions on this?
No, it's pretty clear.
You had it in your math 224. It was just a review. Let me see. We learned, we had another method of finding inverse of a matrix. Anyone can tell me what was that, the other method called? What was the other method to find inverse of a matrix?
Was it the cofactor method?
Very good. You're right. Cofactor method. That is what also in the lab activity last week, you did cofactor method. This was Gauss-Jordan elimination method. This method is preferable. Can you tell me why it is more appealing than that one, cofactor method?
Is it because computers can't do the cofactor method?
Well, computers can do the cofactor method. Yes, they can do that. But the question is, this method is preferable. Gauss-Jordan elimination method is more appealing as it is preferred compared to that one. My question is, why compared to cofactor method, this method is preferable? My question is, why do you think it makes it preferable?
This method is faster in general.
I'm sorry, once again, say that.
Is the Gauss-Jordan method faster?
It is faster. It is true. It is faster. But why is it faster? Why is it more practical for us?
Because the cofactor method uses a lot of determinants.
Yes, you're right. This determinant is a very time-consuming process. And sometimes if the determinant, we have to also divide the whole matrix, once we find the cofactors and the adjoint matrix, and then we have to divide it by the determinant of that matrix. But if even this determinant is 0, then we have serious problems. So yes, finding determinants makes it inconvenient, time-consuming, and if it is 0, again, it is problematic. But this method avoids finding determinant, so it is faster, just multiplying each row by any number and adding. So multiplication addition is the very fast operation. All right, any questions about what we discussed about today? We reviewed this one-dimensional bar element and we looked at the spring element. We found the element stiffness matrix for a spring element, and we talked about global stiffness matrix, and we looked at this example problem. We created this global stiffness matrix by direct stiffness method, and we reviewed some matrix algebra. On Wednesday, we are going to continue practice with solution of simultaneous linear equations. This is the job of Nastran or ANSYS or Abacus or all of these programs, which solves system of equations. But then the preprocessor's job would be to do preparation for finite element modeling, or in post-processing finding stresses or principal stresses like from shear stress or whatever we want. We can, once we solve for displacements, we can find them easily. That is the job of pre-processing and post-processing. For our case, we will use FEMAP and Nastran. We use FEMAP for pre-processing and post-processing, and we use Nastran or Solver. I will give you instructions how to download FEMAP and Nastran, so you can have it for our practice that we start from next week, that we use for solving truss problems, the simplest structures. All right, if no questions, everyone, I stop here. Have a good rest of the day. I will see all of you for the lab on Wednesday. Take care, everyone.
Professor,
Yes.
Thank you.
just to confirm, the only thing due Wednesday is activity 1, yeah?
Activity 1, that's right.
Okay, awesome. Thank you.
At the beginning of the lab, I will tell you, you should have it ready, so to download it or not. I will tell you on Wednesday at the beginning of the lab.
Okay, thank you.
All right, sure.
Thank you, Professor.
Thank you.
Thank you,
Bye.
Professor.
Sure, sure. Bye.